Okay, so next section of notes, I want to talk about the attractive forces. So this is often, like I said, another type of question you're going to get. It's generally tied with the shapes and polarity question. So something to keep in mind is last year when we did structure and bonding, you had a category question on types of solids, and those types of solids focused on the whole range. You had 4 different ones that we were talking about. This year they're narrowing it down to just the covalent molecular, and there's a reason for that because they want you to distinguish between the different types of covalent molecular. Or not the different types of covalent. Yeah, I would say different types. Okay. So what we're thinking about are the attractive forces, and it ties back into the polar and the nonpolar of the molecules. So this year's focus for this question, so the types of solid question is going to adapt. From level 2 is now going to become a question talking about attractive forces of covalent molecular. So that's for level 3. So that's how it's been adapted and how it's growing. So what they're looking for is basically comparing and contrasting different covalent molecules and why they have different melting and boiling points. Something to keep in mind when we're talking about covalent moleculars, say for example water. Two types of bonds that we need to think about for the covalent moleculars. The first bond is our covalent bonds, which are between our 2 atoms. That is holding the molecule together. So our covalent bond is an example of the intermolecular, internal. Sorry, intra. Sorry. Traumatic to break. That's the way. Traumatic. So intramolecular forces or intramolecular bonds, those are traumatic to break because they are holding the molecule together. The other type of bond we are having are the intermolecular bonds. Think of it like international travel. It's the result of, the slight negativity, the slight positivity. No, that one's negative. Sorry, my bad. Slight negative, slight positive. All right. So last year we learned about the intermolecular forces, but we didn't learn about it in detail. This year, we're actually breaking it down to its different subtypes, so that way we can justify what's happening. All right. So first subtype that you are dealing with are the temporary dipole-dipole attractions. And we're starting from the weakest to the strongest. So the name suggests what it is, temporary, which means it only happens for a small instance. So let's say I had 2 nonpolar molecules of chlorine, like that. Here's another molecule of chlorine as well, like that. Now, obviously, these guys have electrons, and they're going to be moving around randomly in these molecules. We know they're being shared equally. Every so often, by chance, the electrons congregate on one side of the molecule. So this is a random occurrence. And very temporarily, that's going to be negatively charged. Now, what happens when this happens is that because this has become slightly negatively charged, it's going to induce other molecules to also very temporarily change their charge as well. So this area of electron negativity, this area of slight negativity, it's going to be like, ooh, I see there's electrons over here, and I'm going to also force the electrons further away because like charges repel. So now it's going to temporarily induce that guy to be slightly positive. And so that's going to, like I said, temporarily form a covalent bond there. Not covalent bond, intermolecular force. Are we okay with that? All right, something to keep in mind. This is more likely to occur when the atoms are larger and if the molecules are larger as well. And that again has to do with the fact that you have more electrons there. So if I was comparing two nonpolar substances, say for example, CH3, CH3 versus CH3, CH2, CH2, CH3, this one's going to have a higher melting and boiling point. Because it has more electrons, the larger molecule, more likely to have that unequal distribution. Are we okay with that so far? All right. Keep going. Watching our time. Try for more colors. All right. Next thing we are thinking about are permanent dipoles, dipole interactions. In this case, we are talking about things that are polar molecules. Dipole forces. So it's what you believe, or sorry, it's what you think the word permanent means. It's always going to have an unequal distribution of charge. I don't know if it's like permanent, right? Watch me spell everything. I'll fix it later. No, I switched around the A and the E. Sorry, guys. See if I spelled temporary right. No, I didn't spell temporary right either. This is what happens when you can't spell. Oh no, temporary. No, I did spell it right. Sorry, guys. I can't spell, so feel better about your spelling. All right, are we good with that? All right, the last one and the most powerful one are just trying to find a color I haven't used yet, are the hydrogen bonds. So this is when you have hydrogen attached to a very electron negative atom. In this case, the only ones we think about is hydrogen attached to oxygen, hydrogen attached to nitrogen, or hydrogen attached to fluorine. Those are the instances it arises. Some things to keep in mind is that hydrogen is a very tiny atom. It's the smallest atom that we have. So when these electrons are pulled away from it, you're actually exposing its positive nucleus and its core. So that is why it has to be hydrogen, and it needs to be attached to a very electronegative atom, so that way it really pulls it away from it and very much exposes that positive nucleus. So that's why it's very specific to that type of relationship. This one is your strongest one. So when you're looking at your comparison of molecules, you're looking to see, do I have a hydrogen bond there? Right. I'm just mindful of the time. Now, there's one more factor that will affect the boiling points and melting points, and that's going to be stackability, so shape. So, for example, a straight chain carbon, like that, is going to have a far easier time layering itself on top of each other and making lots of intermolecular bonds, especially those temporary dipole bonds, versus something that is branched like this. 2, 3, 4, 5. 1, 2, 3, 4. Let's say I had something like this instead. So this one will have the higher melting point and boiling point because it can stack. This one will not. So they will give you a combination of things, so do watch out for that. I'll show you guys some quick, no brain too small questions, but that's the idea for these attractive forces. So here we go. And I'll get a CPR quiz set up for you guys too. Unfortunately, like I said, we have to move on from this. Oh, and I forgot to do boiling point. Okay. The other thing to keep in mind is you see these heating curves and cooling curves a lot. Just keep in mind, sorry, I'll put my level 1 stuff up because they did this too. When you heat a substance, it makes the molecules move faster, and that's increasing the temperature. When we hit this point here or this point here, instead of the energy going into making the molecules move faster, it's going into breaking the bonds. So that's why the temperature doesn't change at this point. Same thing, temperature. So that's the melting point, that's the boiling point. Okay? I'll link in the video that I did with my level 1s because we talked about that with them too. All right? But that's what you're looking at. Alrighty.